Okay, well, hello everyone. I guess we'll get started here. So, welcome to the Forestry Adaptation Community of Practice webinar today. For those of you who don't know me, my name is Annette Morand, and I am the facilitator of the online adaptation communities of practice. And those are run by us here at OKR, which is the Ontario Centre for Climate Impacts and Adaptation Resources. And we're located at Laurentian University in Sudbury, Ontario. So the way the webinar will run is as follows. So after this short introduction, we'll have the main presentation, which will go for about 40 minutes or so. And then at the end of the webinar, we'll have some time left over for any questions that you might have for our presenter. So before we get going, I just have a few housekeeping items to go over. So first, for those of you who dialed into the conference call line, your lines have been automatically muted. And the reason for this is just to avoid any audio distractions or feedback during the webinar. So to ask a question during the question and answer period, all you're going to have to do is dial *6 and that will unmute your line. But please do keep your lines muted during the presentation. Also, you'll notice that there's a chat box on the left-hand side of your screen. You can use this chat box to field any questions that you might have for the presenter during the Q&A session. As well, if you have any technical difficulties during the webinar, you can also use this chat area to type your message, or you can actually click on my name and send me a private message, and I can try to help you as best as I can. I also want to mention that we are recording the webinar today. I'll be sending out a copy of the recording to all those who have pre-registered with me, and we'll also be posting it to the Community of Practice website. And finally, just for those people on the line who may not be familiar with what the FA COP, or the Forestry Adaptation COP, is, I just wanted to take this opportunity just to quickly mention that it's an interactive online community, and it's dedicated to those who are working in forestry or those who are simply interested in forestry and climate change adaptation in Canada. So it includes features such as news articles, events, an online library with lots of resources, various discussion forums, and much, much more. So it's free to join. So if there's anyone on the line who's interested in learning more about the FA COP, please just click on the link in the chat box for more information and to register. So with that being said, we're very excited to have Sue Ziegler on the line with us today to talk about how climate change can accelerate carbon fluxes without changing soil carbon stocks. And just so you know a little bit more about your presenter, Sue is a biogeochemist and professor in the Earth Sciences Department at Memorial University. So during the 9 years that she's been at Memorial, Sue has led the efforts to establish the Newfoundland and Labrador Boreal Ecosystem Latitudinal Transect, with colleagues in and outside of Memorial University, and partners in the Canadian Forest Service and Newfoundland and Labrador Centre for Forestry Science and Innovation. So Sue and her research group are interested in understanding the impact of climate and environmental change on the carbon and nutrient dynamics of boreal landscapes. And their work spans both terrestrial and aquatic ecosystems and is specifically focused on the linkage and interfaces between these environments. So on behalf of everyone joining us, I'd like to extend a very warm welcome to you, Sue, for taking the time to present this webinar for us today. It's very much appreciated. So without further ado, I will now turn things over to you.
Hey, great. Thanks, Annette, and thanks, Jason, for giving me the opportunity to share our results from ongoing research that's happening over here in Newfoundland. Specifically looking at the transformations of carbon and boreal forested ecosystems is kind of what I'm going to focus on today. And more specifically, looking at the observations that we've made related to ecosystem fluxes of carbon within the soil stocks and the composition of those soils as an example of how soil carbon, within one kind of ecosystem type may respond to projected climate change. Having said that, though, having some exchange with Jason and knowing that this is a community of practice on forest, I'll also be alluding to making sure that there's connections so it's kind of clear how the work that we're doing related to carbon and nutrient cycling and influence of climate change actually relates to forest practices and our understanding of forestry resources. So a good title, maybe a subtitle for this would be Implications for Boreal Forest Carbon and Nutrient Dynamics, say, and their potential feedback on climate. So in addition to acknowledging my co-authors, that you can see on the first slide here, who've been instrumental in the work, the main focus of the work that I'm going to present today, I also would really like to acknowledge the group at large. So the efforts and the results I'm going to be talking about today are largely only made possible through a network of collaborations with a good host of hardworking individuals, from students and postdocs to our partners, both in the U.S. and in Canada. And I've got Carrie Bowering circled here because I'm going to present a little bit of her work, which has to do with harvesting impact on dissolved organic carbon dynamics in forest ecosystems as well, kind of connect that to the larger picture that I'm talking about today. And also the funding supports through strategic partnership and project grants at NSERC. Of course, the provincial government support through the Forestry Science Foundation and CREATE, as well as the Canadian Forest Service and technical staff, both here at Memorial and at the Canadian Forest Service as well. So we're all aware, obviously, of the increases in temperature that have been both recorded and which are projected, in the coming century, and the focus of the intense nature of that change, particularly in high latitude systems. For example, in the boreal zone, that coniferous belt of forests that we're all aware of, and where we live in Canada, for example. And in that high latitude region, it's also a region of high stocks of carbon, located within both upland as well as wetland soil. But what's also projected for the coming century is a very large increase in precipitation, again, particularly in high latitude zones as well. And this is another aspect which is very critical to following both carbon and nutrients within ecosystems and their potential impact on the productivity of those ecosystems. And so those are really important implications and factors that we need to actually look at. But when we look at the kinds of studies that have been done, they've actually alluded to a lot of very important processes that are critical and that are responding to particularly temperature or elevated CO2, for example. Lots of really great manipulative studies have been done, which have really targeted and focused our understanding. For example, very dramatic increases in respiration associated with temperature and the sensitivity of that respiration to increases in temperature have been observed in manipulative studies, as well as other types of processes or shifts in microbial communities, soils, and so forth. Those have been very important, and they've also been coupled to very large-scale global observations where we look at respiration, for example, in soils within various ecosystems, spanning very different kinds of ecosystems across biomes. Tropical forest ecosystems versus Arctic tundra, for example. We see very big differences both in rate processes as well as concentration, particularly in the surface soil. And from those, we've deduced a lot of information with how we predict or might predict what happens. However, it's not very clear in the intermediate. So when we're looking actually within a given ecosystem where we don't have those big shifts in the kinds of vegetation that comes with long-term change associated with thousands of years shifting biome, but rather over the next 100 years. So those predictions on those maps from the IPCC report, for example, what's going to happen in a given landscape or a given ecosystem over that 100-year time period? There's going to be a lot of changes in precipitation and temperature over that time, and it's really unclear what kind of changes are going to come about as a result of that. And so there's a little bit of an intermediate gap there, which I think can largely be explored, perhaps using climate gradients. What we do know from the global observations that tell us about long-term climate change impacts, they are linked to vegetation. They are linked to those climate variables. And so what would be interesting or useful, and what we've actually focused our efforts on is looking within an individual type of ecosystem, but where we find that ecosystem in different climate zones. So hence the sort of a traditional trading space for time using a climate gradient. And so the climate gradient that we're working on is in that little red circle in the top left-hand corner on the slide there, Newfoundland and Labrador. So it spans the most southerly point, actually, in our province on the island of Newfoundland in the Grand Convoy Valley. And these are regions where these forests that we've been investigating are balsam fir, moss-dominated forests. And the regions that we've chosen to work in that you see in the map there on the right-hand side actually span watersheds of the largest rivers in those regions. And that's on purpose because the design of this research program is essentially to link the forest terrestrial ecosystem through headwater streams, large river systems, and eventually into estuaries within each of the zones. The furthest north that you go in this climate transect, which is in southern Labrador, at the very top of the map, is Eagle River watershed, which is the most northern extent of the balsam fir dominated forest within this region. So here we're trading space for time along a gradient that is essentially about spanning just over 5 degrees in temperature, and also roughly about a 40 to 50% increase in mean annual precipitation. So kind of in line with that 100-year sort of projection that I was just mentioning earlier in the talk. And the idea here is to investigate the upland forests, which I'm going to focus on today, and the carbon and nutrient stocks that are located there, and the fluxes, ecosystem fluxes associated with those. But we also have headwater stream sites that are associated with those same forest areas. And we have established monitoring equipment since 2011 in 3 forested stands across each of these 3 regions that I've depicted in the map here. The most southerly, the Grand Codroy, the Salmon River, and the Eagle River region. So I'll be kind of referring to them, but they're sort of color-coded, so hopefully you can kind of follow along with the results from this region. So one of the main questions that we had starting off with our work and the establishment of the infrastructure across the site, how climate change may impact the carbon stocks and the fluxes associated with the soil within these forests, and then within these watersheds overall. And so we focused in on how fluxes actually vary, fluxes to and from these soils, forests vary with climate along the gradient. How does the composition of that organic matter in the soils vary, and what does that tell us about the turnover source, the transformations that have been underway in those different environments, subjected to different climates? And if that composition does vary, does it reflect a balance in terms of what's coming into the forest soils as a carbon, into those carbon stocks from the primary producers in those ecosystems? Or does it reflect a net loss or a net gain from soil stock? And so to do this, we've been doing very traditional ecosystem measures of litter fall input, respiration from the soil, as well as dissolved organic carbon fluxes within the soil. So from the podzolic soil organic horizon, the really rich surface organic horizon, to the underlying mineral soil. And I just plugged in here just the relevance to nutrient cycling, which is something we need to look at when we think about the productivity of these ecosystems, forest ecosystems. That while looking at the soil carbon and the transformations of soil carbon, we are largely looking at the reactivity and the transformations of nitrogen and phosphorus, because the majority of those nutrients in these particular systems are actually tied up in those organic matter pools. Including in the watershed, when we look at the dissolved organic matter, that's where we see the nitrogen and phosphorus largely in the stream systems that we're studying. So any of the mineralization, that is the conversion of that organic carbon to carbon dioxide that we actually observe should be linked to the release or transformation of organic nitrogen and phosphorus to inorganic forms that may become therefore more available to primary producers or microorganism systems. So in these different, these replicated sites across each of the landscapes in our transect, we were looking at carbon, nitrogen, and phosphorus input and losses, measuring the productivity largely by diameter at breast height, and the chemical composition of those soil stocks as well in those regions. And you can see in the middle picture there, that's Zimbao Zhu, who's over on the left-hand side, the middle picture. He and students working with him have established both trenched and untrenched collars and plots across each of the sites in each region, and they measured carbon dioxide released from those over a year and a half period every 2 weeks in the region along the transect. And we have passive pan-line scimitars there on the right-hand side, where we're measuring dissolved organic carbon amongst other metrics such as nutrients coming through that really thick organic horizon surface, hitting the surface mineral soil. And we've been monitoring those spanning periods throughout the year, including during snow melt. Those are ecosystem measurements. So to kind of summarize and putting together multiple years here. So the respiration data is over a year and a half, but the DOC data is a culmination of 3 years of data. So it's a litter fall that I can show you results from. But what we see in terms of the respiration rates is sort of what would be expected. You know, we go to the warmer region there in the south, and we have an increase in overall annual respiration of about 40%. And congruent with that, we see DOC movement from the organic horizon to the mineral soil through these lysimeters, actually increasing threefold from the cooler Labrador northern site to the wetter, warmer Grand Convoy site on the right-hand side. So lots of mobilization and losses here that we've observed with respect to carbon systems. And this is congruent largely with litter fall input and trends that we see in the tree biomass relative productivity as well. And the increases there are very large between the coldest and the warmest site, and much more variable and quite large and intermediate site because we've got wind throw storm activity in that peninsula site. So despite the fact that we've got those accelerated fluxes, however, both coming in and being lost from the soil horizon, the stalks themselves, which are depicted here in the dark brown and that sort of lighter brown color below it, stacked bars on this diagram, don't really exhibit any significant differences among the regions. And the only difference we do see is actually a larger stock of carbon in the two warmer regions relative to the coldest regions as the organic horizon stock of carbon. So we don't see much variation in that. So there's no evidence that there's significant loss associated, even though we've got 40% loss of carbon dioxide here. So largely, it seems like those inputs are doing are balancing out those losses to a significant extent. You know, what's really interesting is we measured the radiocarbon in the surface mineral soil across all the plots in each one of the 3 sites in the region. And these values that I'm showing here are the average radiocarbon value, and then I put the mean age associated with that radiocarbon signature for the mineral soil carbon pool there for each of the regions. And you know, despite the fact that the signature in the Grand Convoy region is extremely modern relative to the Eagle River, that suggests that we have tremendous turnover. You know, specifically, especially considering the stock sizes and the lack of real change in the fact that increased stock size that we see in Grand Convoy with that wetter and warmer climate. So it's really congruent with a very significant increase in turnover. And again, in the middle there, we have our messy value of the intermediate site where we have a tremendous amount of wind throw, where we've actually lost one of our study sites completely due to windstorm activity. So that younger age was really intriguing to think about as we were digging into our results. And we sort of asked the general question of how long it would take. We're trading space for time here among these sites in these different regions. How long would it take for that coldest climate, the coldest climate soils there in Labrador, to look like the radiocarbon signatures that we observed in our warmest study region if we applied those accelerated fluxes that we've actually measured in the warmest region? How long would that actually take? And largely what we see when we model that, I'm not going to show the results of this, but there's a really nice soil art called modeling procedure that you can apply to radiocarbon analysis of soil to actually, you know, explore these kinds of questions. And what we determined from that is it looks decadal. So it looks like it would take on any order between 20 and 60 years of that kind of a warmer climate and those fluxes that we measured to be applied, get that younger signature that we observed in the warm climate in those colder climate soils. So the observations that we're making across this gradient seem to be congruent with the kinds of changes that we might expect over decades. So kind of within that sort of century timescale that we were kind of looking for. So in addition to looking at the radiocarbon and linking that up with those carbon fluxes in these ecosystems, we investigated the organic matter composition of the soils in these ecosystems as well. And we used a number of different analyses from elemental ratios to stable isotope analyses, NMR to look at really broad organic carbon functional groups, and amino acid composition. So the amino acids can be a very bioavailable component, and the changes in amino acid composition can tell us something about the degree to which the organic matter has degraded or diagenetically altered. How much has it actually been worked through by the microorganism soil in relationship to the mineralization or loss of carbon. So what we typically see in soils in general, people see this a lot, is with carbon to nitrogen ratio, you typically see an increase with depth. And what I'm showing here, arrow here, sorry. The carbon to nitrogen ratio here, and all these figures here are depicting the litter fall. So this is the actual composition of what is hitting the surface of the soil. And then the L, F, and H are the top, the middle, and the bottom units of the organic horizon. And then the top 10 centimeters of mineral soil is the B horizon I put down. So this is a sort of a depth profile, and also including the litter fall here. And so carbon to nitrogen ratios will typically drop through a soil profile due to the utilization of carbon-rich substrates like carbohydrates and immobilization of nitrogen. That's pretty understandable to see that. The carbon-13 ratios typically increase, and that's what we've observed here. These are the data from the Labrador, the coldest site. And this is due to basically the loss of plant carbon and increases of those microbial inputs. And alkyl to O-alkyl representing plant waxes relative to more labile carbohydrates like cellulose, hemicellulose coming from those plant materials. They typically increase, but we don't see a lot of that associated here, and we think this has to do with moss input, but we certainly see an increase when we get to the mineral horizon, typical of soil profiles. And this hydrolyzable amino acid degradation index is basically using a principal component analysis of the amino acids that we've observed, their relative abundances, and how those are actually distributed from fresh plant material to the most degraded components, indicating increasing degradation here with a more negative number. And so that looks congruent with what we see in the soil profile. If we look at this across our regions along our climate transect, despite the fact that the younger soil organic pools are found in the warmest region, they actually appear as diagenetically altered as organic matter that's up to 300 years older. You know, it's showing that radiocarbon from the mineral soil sort of suggests that big age difference that we have, mean age difference in these organic matter pools. So despite that big age difference, we actually see, if anything, a more degraded signal here associated with the warmer region, or no real change at all. This is a more degraded signal, again, for that warmer region, and again, no real regional change at all. It's consistent, except maybe right here. So there's really not a whole lot of difference, especially considering the big age difference in this organic matter across the gradient, which was pretty interesting to see, but suggests that rapid turnover and that importance of new input in those warmer soils. And in addition to thinking about the carbon chemistry and carbon turnover, well, we have a similar story in terms of the extent of soil organic nitrogen diagenesis across these regions. That is, we see that percent nitrogen as total hydrolyzable amino acids as amino acid, which is a really nice metric for the bioavailability, but also the degree to which the organic matter has been exposed. as organic matter is decomposed, those amino acids are lost, and the nitrogen that we see remaining in organic matter is largely either uncharacterizable or more heterocyclic, and it's not in the form of amino acids. So it's reduced as we go down through the depth, and particularly in the older carbon in the soil. But we don't see any regional differences here. So despite over 300 years difference in age, we've got a similar extent of soil organic matter diagenesis, suggesting that in those warmer climates, you've got an increase in the turnover of that nitrogen coupled with that carbon, and may suggest increases in nitrogen availability in the forest. So kind of in sum, thinking about the carbon here, and largely just in these intact, mature forests, when we look at my arrow here, as we increase temperature and precipitation congruent with about the projections for the next 100 years in these particular types of boreal forests, we're observing very big losses of carbon via soil respiration, large transfers of carbon through the soil as dissolved organic carbon, but also a very large input of carbon. And the fact that we have decreasing radiocarbon age and increasing state or degradation and turnover organic matter suggests that those inputs are keeping up with the actual large losses of carbon, either out into the atmosphere or down through the soil profile and perhaps off-site through the aquatic environment. So capturing those carbon, these ecosystem stocks of carbon and the fluxes across this forest climate, this climate gradient of forest ecosystem, really provides us with an example for different ecosystems, but also for the region that we definitely see these enhanced carbon fluxes and turnover of carbon stocks in these high latitude ecosystems associated with the kinds of climates that's projected for these regions in the coming decades. But despite that acceleration of carbon dynamics, carbon fluxes in and out of the soil, the stocks of carbon themselves appear to be maintained. And they actually really mask the extensive turnover. When we look at the chemistry of those organic matter pools, they look real similar. And that's kind of masking that sort of rapid turnover and degree of diagenesis. And we only really understood that by looking at the radiocarbon and coupling it to the fluxes that we see in the ecosystem. And overall, what this ends up demonstrating for us is that the stocks themselves can remain constant within an ecosystem type and in these kinds of boreal forests for several decades prior to any kind of shift in the ecosystem into a different type of regime, different vegetation associated with longer-term climate change. So what about forest management practices when we think about the coming century and think about results from a study like this? There's a lot of interest right now. So this is just an example of an article that just came out, I think, in the last few weeks, looking at the connections of the landscape. So forested landscapes in the boreal in relationship to surface water dissolved organic carbon. And the take-home message of this paper is that climate and forestry effects can actually be additive, but primarily at the landscape scale. We've gotten interest in that in our study sites, both in terms of a localized region that we'd like to upscale more so into the climate transect itself by studying a forest harvesting experimentation site. And this is work that Carrie Bowering, who's a PhD student here in environmental science, is really focusing in on. She's put a lot of effort into a experimental site which is nested within a watershed that we're currently monitoring outside of Corner Brook, Newfoundland. It's in Pinns Brook. It's in that Humber River watershed that I showed you, sort of a middle region within the climate transect we're working in. And this is an experimental site that consists of 2 hectares of mature black spruce stands that are divided into 8 plots. These are 50 by 50 meter plots. 4 of them in those plots actually were clear-cut back in 2003. And Carrie actually installed passive pan lysimeters to actually look at the movement of dissolved organic carbon through the organic layer to surface mineral soil. She's installed a pair within each of 3 forested as well as 3 harvested plots. and actually made measurements on a weekly to 2 weeks, every 2 weeks, over a year and a half period to capture the dynamics of both dissolved organic carbon, nutrients, in relationships to hydrology. So those passive pan lysimeters have been sampled basically on a frequent basis in order to capture unique periods of hydrology. And she's currently monitoring the greater watershed within which this experimental forest is captured within, in order to best link the landscape level dissolved organic carbon to what she's observed in the forest itself. But what I wanted to do is just provide you guys with a little insight into what she's found in relationship to this picture of carbon stocks and in relationship to nutrients within these forest ecosystems. And when she looks at the annual average of her data over this 18-month period, which includes the snowmelt period, she sees that the DOC flux themselves is actually greater. So this is the grams of carbon per meter squared essentially per year. It's her study period, it's a little over a year. That amount of carbon that's actually lost from the regenerating or harvested sand is significantly greater than what's observed in the mature forest. But it seems to be largely driven by the water flux, which is also significantly different, but not the DOC, which is different, but in the opposite direction. The DOC concentration of the water in those forest soils. And what's important to note from this is that, yes, hydrology is important. The amount of water coming through that environment dictates the loss of organic carbon, but the actual organic nitrogen and phosphorus that goes along with that material, which is also what she's looking at. And I'm not showing here. But the important thing about one of the important aspects that she's actually learned from her research, shown here, which is the DOC flux measurement for that harvested sand shown in the light colors along here. You can see the responses of that flux to precipitation and soil moisture dynamics. Follows very nicely with that, and that there's generally higher values in those regenerated sands throughout the year. And they seem to be responsive to that elevated moisture in the soil and to precipitation down. However, when we look at the snowmelt period, when she actually captured this flux right after the snowpack melt, she shows the snowmelt material here in these little bar graphs here, the snow melt amount bar graph here. The increase in the water flux here wasn't really congruent with any real difference between the regenerated and the forest sand, suggesting that the snowmelt period represents obviously a very hot moment because there's lots of water draining through the landscape, but doesn't seem to play out in terms of an interactive effect, increasing DOC or dissolved organic nutrient losses from these forests at that particular time. So it represents a time when harvesting impact may actually be reduced. So something that we're wanting to follow up on. So the understanding of hydrology is required to capture the sort of the combined impacts of what we do in terms of harvesting and the projected climate change processes, both precipitation and temperature. So transport and potential losses of organic carbon and the nutrients that go along with those, with the organic matter, is hydrologically controlled. But it's the temporal nature of that control which really is probably very important. It suggests that when we look at projected changes in how precipitation occurs, if it is in fact increasing precipitation over the course of the year and decreasing snowpack and therefore snowmelt, we may actually be looking at a greater impact of that hydrology change that occurs with harvesting activity on the transport and movement of nutrients and carbon off the landscape. So just to conclude, I've made mention of these findings with regard to losses and inputs. What we've found from Carrie's work is that there might be like a 25% further increase of harvesting, but the additive effect of that increased rainfall, potential decreased snowpack, is also suggested by the temporal nature of what she found, and something that we have plans to look at further, in addition to the kind of processing that's happening within the landscape. So with that, I thank you very much for your attention, and I'm hoping there's some questions, and I didn't move through that too quickly.
Okay, great. So thanks so much, Sue. So we now have some time for any questions, obviously. So if you have any questions or comments, again, if you'd like to use the chat box, please feel free to go ahead and type out your question there. If you're on the conference call line with us and prefer to ask a question to Sue over the phone, all you're going to have to do is hit *6 and that will unmute your line. So I see some people typing. Are there any questions on the conference call line at the moment? If so, please go right ahead. Okay. If not, I see some people typing. But I have a question, Sue, just in the meantime. So given that soil carbon stocks are stable across the climate gradient studied there, can you comment on the implications of that finding more generally for boreal forests or boreal forest watersheds?
Yeah, the carbon stocks that we observed in this forest, these are relatively music forests, and the reason for looking at these was actually to look at systems that weren't moisture limited. So I think one thing that's really important to consider is the relative balance in terms of evapotranspiration and precipitation that's coming into the ecosystem. And that's going to largely impact both productivity and respiration. In these systems, there's no moisture limitation to either of those activities. And so it's a good example to show that there's potential for this. But then we actually have to start accounting for other dynamics in other boreal ecosystems. So the interior of Alaska or interior of Canada, there's other issues with regard to moisture and precipitation regime. I think they'll be really, really important to couple with this kind of information. And within the watersheds themselves, that's also very relevant in terms of the extent of runoff versus evapotranspiration and the degree to which that happens in wind, and hydrologically speaking. That's going to be very important for dictating the overall carbon balance within different forests.
Great. Okay, thank you. So we have a question from Barrett in the chat area. So, so how do you take care of root respiration while measuring the soil respiration?
Yes, that's a great question. Zimbao Zoo actually did trenched plots and untrenched plots to sort of get an understanding of what that relative difference may be, though there's all kinds of issues, obviously, with doing that. The data that I was showing you guys today is actually just open respiration, so it includes root respiration, because our goal in this case was to look at the total loss of carbon relative to all inputs. And so that would actually include that that component of plant respiration. So that's something that Zimbao Zoo is looking at in relationship to the climate in these different ecosystems, is the relative rate of root respiration relative to total respiration, which appears to be a lot lower based on these trenching experiments that he's conducted.
Perfect. Okay, thanks, Sue.
I hope that helps for us.
I see some other people typing here, so we'll just give everybody a few minutes.
Okay, you're welcome.
While we're
done this before, where you had typing questions in.
All right, so John Liu from the MOECC. So can I interpret your research conclusions as climate change may change the carbon flux, but not the stock and soil for decades?
Yeah, in these forest ecosystems, that is what our findings indicate. And I think it's important in a lot of ways because it demonstrates the fact that accounting for the inputs obviously is really important, and we all know that. However, I think in going forward, the fact that it's demonstrated for these ecosystems lends to the next step of investigating really important factors. So then what controls stock in other kinds of boreal forest ecosystems? As I was mentioning to Annette's question, a lot of this may come down to the different kinds of precipitation regimes, moisture regimes, which then can be limiting primary producers. If you have issues with extensive evapotranspiration and a limitation of moisture coming along with this, then the conclusions might be very different for different forest ecosystem types. So yeah, I think you're right. You got it. Thanks for the question.
Great. Thanks, John. Okay, I don't see any other questions being typed out, but I'll do a last call for any questions on the conference call line. So if you have any questions, please go right ahead and hit *6 to unmute your line. And then I guess also last call for questions in general, if anybody has any in the chat box as well. If not, I guess we will wrap things up here. So thank you to everyone who joined us today for the webinar. We hope you enjoyed it. Obviously, a very, very big thank you goes out to you, Sue, for your time and effort. For
yeah, it was enjoyable. Thanks.
Yeah, it was great. So any last comments from you before we sign off here?
I guess not. It'd be nice to see faces so I could actually have a more conversation. But no, I appreciate people's attention. It's great to have interest in our work, and it's great to have an opportunity to share it too.
Absolutely. So are people able to, if they have any follow-up questions, can they reach you via email? Is that okay with you?
Yeah, that's fine.
Perfect.
My first initial S, and is it on there somewhere?
You know what? I'll CC you on the emails after, so everyone will have your email address as well.
Sure.
Or you can type
it in. No problem.
So perfect. Okay, well, thank you again, everybody, for joining us, and have a great week.